So here we're working with Algebra 2 with trig and Unit 5A.2. These are properties we've learned before, but now we're discussing these with our rational exponents. Fractional exponents are rational exponents. So here, when the bases are the same, we multiply two bases that are the same. We're going to add the exponents. So that's a property we've done before. So now here we're going to take our y with our 1/2 plus our 1/3. We're adding the exponents together. And of course, what we know from before is that when we add exponents, we have to have common denominators. So in this case, the number that both 2 and 3 go into are going to be 6. So you have to multiply the 2 by 3 to get it to be 6. So you have to multiply the top of the fraction by 3. 1/3 has to be multiplied by 2 to be sure to get your common denominator of the 6. So your final result is y to the 5/6. We added the exponents together. That would be the same result as multiplying with those rational exponents. When we raise a power to the power, this is where we multiply exponents. So the same thing goes with rational exponents. We would take 1/2 times it by 1/3. Here, with multiplying fractions, you do not need common denominators. So this becomes 1/6. When you have parentheses with an exponent on the outside, but this has to be a binomial. Oops, this has to be a monomial, not a binomial. A binomial could be a plus b. A plus b, or even a minus b, you could not distribute. That's what we talk about most every day. Here we can distribute because there is not a plus or a minus in between our terms. So this is a to the m power times b to the m power. So you'll be able to convert back and forth for whatever's more appropriate. In this case, we would distribute the 1/3 to both of these, and we get 8 to the 1/3 and x to the 1/3. To the 1/3 power. 8 to the 1/3 power is saying the same thing as a cubed root of 8. You could convert that over to radical form, and that would be the cubed root to the first power, and this is still the cubed root of x. So you could put an x inside there, you could leave it out, but I'm just trying to show you that 1/3 or 8 to the 1/3 power is the same thing as 2. Now I'm choosing to leave it with the fractional exponent because the question was written with a fractional exponent. So if there's a choice to which method to leave it, we're usually more confident using radicals. So you'll see us convert it over to radicals a lot. I want to be sure you understood why 8 to the 1/3 was 2, because the index is the denominator of your rational exponent. But when it comes down to a final answer, if the question is made with fractions, then have your answer with fractions, unless, of course, it states otherwise. Next, we have a negative exponent. We're all pretty good at that. So that means you're going to write it in the denominator. So the same thing goes with a negative exponent if it's a fraction. It's still going to take the x and put it into the denominator with a positive exponent. Typically, we don't leave radicals in the denominator, but in this case, just showing you with the negative exponent what you can do. A to the m power, a to the n power, the bases are the same. The exponents are different. We can subtract the exponents. So in this case, we get y to the half power minus 1/3 power. Again, with subtracting, you have to have common denominators. So 6 will be our common denominator. To get the 2 to become a 6, you had to multiply the top by 3. To get the 3 to become a 6, we had to multiply the top by 2 also. So 2 times 3 is 6, so 3 times 1 is 3. Now we're ready to subtract. So we get we get y to the 1/6. Same as we did earlier, when you have the parentheses of a fraction, we can distribute in, or you could even pull out backwards. But in this case, we're looking at how to distribute that in. Here it has the same exponent. You can pull it out, or you could place it inside and they would have the same. So the same thing goes here. So this is going to be x to the 1/3 power and 8 to the 1/3 power. Well, we know the 1/3 power means the cubed root. So this is the cubed root of 8. And we get 2. The top of the fraction, it can't be simplified at all. We could write it in radical form, but because the question started out with fractional exponents, we'll leave our answer in rational exponents. Here we're in radical form. We could separate the problem. It's not a 4, it's an n. So if you have the bases the same, you can put them together into one radical, or if they're in the same radical, you can pull them apart, however you like to do it. So here, one way we could talk about this is to separate, to have 40 and x to the 5th. Well, 40 breaks down into 8 times 5. 8 is known as 2 times 2 times 2. That's 8 times 5. That's your 40. And the cubed root of x to the 5th. Well, x to the 5th is made up of an x cubed and an x squared. So if you don't want to write out all the x's 5 in a row, you might just either visualize it, or you could physically write it to help you stay organized, that you have a group of 3 and then you have some left over. We have a group of 3 of a kind, and that's what we're looking for with a cubed root. So we know we're going to have a 2 come out. We're going to have an x come out because we have 3 of a kind there. In the cubed root, we still have a 5 and an x squared. Here, when you have a giant All right, giants. Anyway, you have a fraction inside of a radical, one big radical. You can break it apart into two separate radicals. Now, sometimes you have two separate radicals with the same index. That's the important part here. And you find out that A and B can be reduced of each other. So if you have a 12 and a 4, you can put it into a combined format where the 12 can be divided by the 4, and you simplified it down. It doesn't even matter what the index is. You can simplify those. Over here, the A and the B are not simplifiable. X, 8 doesn't go into X or vice versa. But if we had the cubed root of X and we have the cubed root of 8, the cubed root of X over 2, because the cubed root of 8 we know is 2. 2 times 2 times 2 makes 8. Now, because the question started with a radical form, it would be appropriate to leave your answer in radical form. So those are your different properties. So now when we practice these, we look at what the properties are to see how we can simplify it. Now, there's often multiple ways for you to write out your work. You should do some work. This is 125. I completely understand if you do not say 5 times 5 times 5, because that is 125. If you know the cube root of 125, if you know your power chart well enough, so 5 cubed is 125. Then the cubed root of 125 is 5. And we've definitely talked about how 2 cubed is 8. So for your work, it would be appropriate to write 5 times 2 equals 10. If you need to write these out to keep yourself organized, that's okay. But at least you would say 5 times 2, not just a magical 10 answer. I do it in my head. Be sure to write out something. Here, we could work out a way that we could pull out maybe a group of 5 of a kind out of 96. Maybe that's possible. But what I'm recognizing is their indexes are the same. And 9 and 6 are both divisible by 3. So I'm expecting 3 to go into that 32 times and 3 to go into that 2 times. So I've already done some reducing. Now, if you know your power chart, you see that 2 to the 5th power is 32. So that means it takes 5 2s to make 32. 2 times 2 times 2 times 2 times 2. So that becomes 2. If you need to write them all out, you're welcome to do that. All right, for us to simplify, we have to reduce it as much as possible. And sometimes we look at it. We look on our power chart for the number 104, and it doesn't. It goes from 81 up to 243. Doesn't hit any hundreds in there. So something weird's going on with this one. So let's try breaking it down by any number that we're aware of. Well, I see that it's an even number. So I know that 2 goes into it. 2 goes into it 52 times. Well, 52. I know that 52 is an even number. Well, I know 26 is an even number. So if you don't know that 8 times 13 is 104, then you just break it down by factors that you're familiar with. Now you have 3 of a kind. So there's your 2 and your cubed root. Don't lose your index. That's a common mistake. 13. The 13 stays inside the radical. 432. Well, what I notice about 432 is that 4 goes into 4 and 4 goes into 32. So 4 times 4 goes into 4. Once 08. So 4 times 108 is 432. 4 goes into 4 once, and 4 goes into 32 8 times. Well, here we are with this 108. Well, 4 itself can be broken down. 108 can be broken down. Notice how I make the check mark of the radical first. And I've got 2 times 2 times 2. And then I have 9 times 6, or 27 times 2. Well, there's 3 of a kind you might know of. And the cubed root of 27, we know from our power chart that the cubed root, working backwards, of 27 is 3. That's how you would read that. 3 cubed is 27, but 27, the cubed root, is 3. So we're going to have a 2 and a 3 get pulled out. That leaves us with a 3 as an index, and the only thing left is that extra 2. So that's going to give us a final answer of 6. You multiply what's on the outside. Cubed root of 2. $96. Again, 96 is not one of the numbers on our power chart. So there's a couple different ways we could do this. You might realize that 3 goes into 9 and 3 goes into 6. It's a good way to make it a little bit smaller. Oh, there's the 32. 32 is one of those numbers. So the 5th root of 32 is 2. We are doing the 5th root. So if you want to keep writing it out, or if you start to pick up on those patterns, you have a 2 and the 5th root of 3. You pulled the 2 out. That 32 became a 2 because the 5th root of 32 is 2. $162. That looks like 2 times 81. Now I remember 81 was on the power chart. The power chart has 81 down here as 9 squared, but this is the 4th root So we probably want to look underneath the fourth root for that 81, and there it is. So the fourth root of 81 is 3. 3 times 3 times 3 times 3 is 81. So you don't have to write out so much work if you know what your powers are. Now it gets a little bit more complicated. First side was a little basic, just simplifying down. Now we have to start thinking. So let's just take two random terms, like 3x, I guess they're not totally random, and 5x. They're like terms. They have the same variable. So if they are connected to the same term, you can just add your coefficients. So 5 plus 3 is 8 with the x. It's not x squared, it's not 2x, it's just 3 apples plus 5 apples equals 8 apples. So when we come down here to letter A, we see the fifth root of 12 and the fifth root of 12. Those are the same. So they're like terms. So we have 7 minus 1. If its number's not written in there, it's just a 1. So 7 minus 1 is 6, the fifth root of 12. But what if we don't have like terms? So if you don't have like terms, you have to break these down. You need to know what goes into 48. Well, you might know 6 times 8 is 48. And you might know that 3 times 25 is 75. Still nothing matches. You don't have any like terms. Well, this becomes 2 times 3, that's 6, and 2 times 2 times 2, that's 8. And of course, you know 3 times 5 times 5. Well, it's not a 3, I'm sorry. These aren't cube roots, these are square roots. If no number is written in the index, if no number is written there, that means it's a 2. You have to put a 3 if it's a cube root. You have to put a 5 if it's the fifth root. But if nothing's written, it's just a 2. So you're looking for 2 of a kind, and you even have another 2 of a kind. So that's a total of 2 times 2, which is 4. And 2 of a kind, which leaves you a 5. Now you've got your like terms. So you have your 5 and your 4. Your 4 plus 5 is 9, and they're both root 3. Here we have 81. Well, I'm pretty sure I remember on our power chart that we had 81. That was 3 to the 4th power was 81. So I know that this is 3 to the 4th power. So you can write 3 to the 4th power if you want. That helps you organize things a little bit. And 24, you know that that's 8, which is 2 cubed. 8 times 3. Now you're looking for 3 of a kind. Well, there's 4 of them here. So you can pull out a 3 out of those 4, and you have 1 of them left inside. Don't change your, oh, I did change it. Don't change your index. Keep that index the same index. Here you pull out what you have in common, your 3 of a kind. Now you have the same index and you have the same radicand. They're like terms. So it's 3 minus 2, which is 1. You don't really need to write the 1. So it's the cubed root of 3. You could test that. All right, it is possible if you're doing some of this homework and are wondering if you're doing things right, you could take the cubed root, which is number 4, the cubed root of 81, and you're minusing the cubed root of 24, and you're going to get some crazy decimal. We don't want the decimal. Don't write a decimal as your answers. But if you want to check your work, you can see if your answer matches what the beginning was. And you see the decimal versions are the same. So yes, this is equivalent.
Mr. Weber?
Yeah.
How do you get another number besides the 3 in front of the radicand?
All right. When we're looking at a number in front of the 3 on the calculator, if we wanted to do the cubed root, we hit the math key, and we've got 4 as a cubed root, but that's kind of simple because that's one of the options right here. So you can do the cubed root. But what if you want to do something other than the cubed root? Like you want to do the 5th root. So you do the 5, you hit the math button, and you come down to the 5th one, which has the X as the index. And that made that 5 that you originally typed as your index. And then you can type in your number and you can see whatever it breaks down to be. So that's a way to change your index value on your graphing calculator. But no decimals, just check and work. All right, so now we come to letter D, and we notice that the radicands, the part inside the radical, they're different. We can't do this if they're the same. I'm sorry, if they're different, we can't do that. We need them the same. So we're going to look at 405 and try to break down 405. I kind of see the 40 and the 5. All right, so I'm recognizing that 5 goes into 48 times. So 81 goes into 8 times, and then there's the 5. So 5 goes into that 81. And then 80, I'm going to use the 5 again, because if I have a factor out here that's 5, that's 5 times 16. Well, we've learned that the 4th root of 81, we don't want to write them all out. The 4th root of 81 is 3. So I'm going to bring the 3 out, and I just have the 5 sitting inside. I don't want to write them all out, but I know the 4th root. If you're not really sure, you can at least go to your chart and be looking down the 4. Look down the 4th root and look at your numbers. We have 16, we have 81. Those are the 2 numbers that we're using right now. So the 4th root of 16 is 2. We're the 4th root of 5. So you need to simplify those down so you get 2 radicals with the same index and the same radicand. This becomes 6, because you got to multiply them if they're on the outside. Now you're ready to add the 2 together, which is 8 times the 4th root of 5. 4th root of 5. Now, when we're working with radicals and simplifying out variables, there is an issue. Because a variable can be positive, it can be negative, it can be zero. Sometimes absolute values are needed when simplifying. But we're just going to assume that all the variables are positive, so we don't have to worry about absolute values. You'll deal with that in the future. So here, we're going to start to break some of these down. Here's 625. I kind of remember about a 625. So I come back here at 625 and I found it. 625 is the 5 to the 4th power. So the 4th root of 625 is 5. So the 4th root of 625 is 5. And I still have z to the 4th, z to the 4th, and z to the 4th. That's a total of 12 z's in there. 12 z's. I want 4. I want group them up as 4 at a time. I could write them out the long way, or you can just visualize in your head 12 divided by 4. How many groups of 4 are there in 12? And you'll get 3. So it's z cubed. You have 3 sets of the z's with nothing left inside. There's no 5s. There will be no more z's. So there's no more radical. In this case, we know that 32 is 2 to the 5th power. We also have m to the 5th power. We also have n to the 30th power. Well, we definitely don't want to write that out. We have the 1/5 sitting on the outside. Well, there's a property we learned about where we can distribute. Since this is a monomial, there's no adding and subtracting in between the terms, we can distribute that 1/5 in. So when we multiply, raise a power to the power, we get 5 over 5, and m 5 over 5, and n 30 over 5. 30 times 1/5, you only multiply the top. 5 times 1/5, you only multiply the top. So that's why it's these. And those can be reduced to the 1st power, m to the 1st power, n to the 6th power. Here, a couple different ways we can think about this one. You can think about this as the 6th root of r to the 6 and the 6th root of s to the 18. So you're looking for groups of 6 of a kind. Well, there are 6. There's 6 of the r's. So I know I have an r to be pulled out of that. They're 18 divided by 6. If you were to write this in fractional form, it would be 18 because that's your exponent, and 6 because that's your index, which is your denominator. 18 divided by 6 is 3. There are 3 sets of 6 in 18. So I draw my S, and I sometimes put little lines on the edges because it's difficult to tell if that's a 5 or an S. Now, this one is crazy. This one's a little insane. You just got to take your time and you do what's there. You only work with the letters that are the same, kind of your like terms. So the 8 and the 12, they're their like terms. I have K on top and bottom. So that means that we are going to subtract exponents. When they're on top and bottom, you subtract the exponents. M to the 5th power. There's nothing on bottom with the m, so Nothing to reduce with. The D on the bottom is negative. So it's going to be coming to the top to become positive. So you have an extra one of those on top. Now you got to do the math. 4 goes into 8 twice. 4 goes into 12 3 times. So we reduce those. We need common denominators of 2. Nothing you can, oh, that's a K. You got to get the K in there. Nothing you can do with the M. D, you need common denominators. So this becomes a 2 with the K and 1/2, an M with the 2/5, and a D with the 5/3. There is one version of the answer where you could simplify the D down because there's more of them than are the groups that you need. There's a group of 3 in there. There's 5 total. There's a group of 3 in there. So you could write the answer as 2, pulling the D out. You'd still have K to the 1/2. You'd have M to the 2/5. You would have 2 left over after you pulled 3 of those out. I don't know which set you like better. This is a little over the top. So either format in those answers would be fine. All right, this is a little bit easier of one, I believe. Here we have a 56 and a 7. We have an A on top, which is like to the first power. Nothing's written there, so it's a 1. Minus 5/6. Then we have a B. It has nothing to compare with. And we have a C that has a negative exponent. So I'm going to write it on top of the fraction. You can draw that line if you want, whatever. 7 goes into 56 8 times. This would be 6/6. So 6 minus 5 is 1/6. Nothing's happening with the B and nothing's happening with the C. So there's no denominator to deal with. Over here, one way you could break this down is you're looking for 3 of a kind. So you're looking for 3 X's and you have an extra. You're looking for 3 Y's and you have 3 sets of those 3 Y's. 3 plus 3 plus 3 is 9. When you're multiplying, you add exponents. So that's 9, not 3 times 3 times 3. That's not 27. And then 4 to the third, 4 to the third, 4, or Z, I guess, 4 different times. And then you would have an extra pair. So that's one way you could do it. Now, that's not very 11th grade math like, but it works. And if that's what you have to start with, and then you get more confident as you're moving forward, what you can do is say 3 goes into 4 how many times? 3 goes into 4 one of the times with an extra X left inside. That was the X cubed came out and you had 1 X left inside. 3 goes into the 9 3 times. Goes in there 3 times with nothing left over inside. 3 goes into 14 4 times. Well, there's your 4 of them with 2 Z's left over. If that's 12, You have 2 left to get to 14. 2 left inside is your 2 left. Your 6 you never touched. There's your answer. Here, the P and the Q, they don't reduce from each other. They're different variables. So you might consider this as P to the 12th power, 7th root of P to the 12th power, 7th root of Q to the 14th power. Well, 7 goes into 12 one time, so you're going to have a P, because it goes in there. There are 7 of them in there, and there are 5 left over. So that's your total of 12. And on bottom, 7 goes into 14 twice. So you have P over Q squared times the 7th root of P to the 5th. All right, we finish up here. Here we have like terms like we did before. So 18 minus 11 is 7, and our indexes are the same with the radicand, so they're called like terms. So it's just 7 root 3u. Letter B, those are like terms because A to the 4th matches, B to the 2/3 matches. So all the variables are exactly the same. We're adding these together. So I got 15 plus 8, which is 23, A to the 4th, B to the 2/3. Then our last set, this is the tricky one. Now these don't match. We need the insides and the indexes to be exactly the same. We're not changing indexes, but we are changing the radicands. We are talking about how to get them the same. You typically have to simplify it down. We're looking for 4 of a kind. There's more than 4 of the S's in here, right? How many S's? There's 7 of them. So there's 3 extra. So if I take my 10, I'm going to have an S that comes out, and I'm going to have 3 extra left inside. There's 4 of them, and there's 3 more to get to my 7. Minus 18, or 80, sorry. 80 is 5 times 16. And we know that 16 is a number we talked about on our chart. That is the 4th root of 16 is 2. We are talking about the 4th root. So this is made up of 2 to the 4th power. So 2 to the 4th power, you're going to be able to bring out the 2 with the S that's out there. You're going to have a 5 left over and an S cubed sitting out there. So that worked out. Now we have an S and the 4th root of 5s cubed, an S and a 4th root of 5s cubed. Those all match. So 10 minus 2 is 8 with the S and the 4th root of 5s cubed. You don't have 4 of a kind left over, so there's nothing else you can simplify. And that's it. Good job.